Welcome to Propeller Breeze, the show for student pilots, sim fans, and everyone chasing that first solo and beyond. All information in this podcast is for entertainment and general knowledge only. Always verify with certified flight instructors or regulatory authorities before attempting anything mentioned here.
Okay, so you're planning that cross-country flight, temperatures are dropping, the single most dangerous thing you can run into up there, ice. It's just, aerodynamic poison, isn't it?
Absolutely.
Yeah.
It adds drag, kills lift.
Yeah.
You really have to respect it immediately.
Today we're doing a deep dive that's, I think, essential listening for every pilot. But especially if you're a private pilot, maybe looking at planning flights in that cooler weather, we need to unpack aircraft anti-ice and de-ice systems.
Yeah. Our goal here is kind of twofold. First, let's nail down the basic difference preventing us versus getting rid of it once it's there.
Right.
And second, and this is, really the crucial bit for most general aviation pilots listening,
Yeah.
we have to hammer home the pretty severe limitations you find on most light aircraft.
Mm-hmm.
You absolutely need to know what your plane can handle, and maybe even more importantly, what it just plain cannot when we're talking structural ice.
Okay, definitions first then, because people mix these up all the time, and they really shouldn't. Anti-icing. That's the gear designed to prevent ice forming.
Yeah.
Operates beforehand.
Exactly, yeah. It works ahead of time, continuously.
Yeah.
And then de-icing. That's for removing ice that's already stuck on there.
And these systems, they protect more than just the obvious leading edges, right? Wings and tail.
Oh, yeah. We're talking pitot tubes, static ports, fuel vents, stall warning sensors, windshields naturally, and propellers too. Can't forget those. Some planes even have special ice detection lights for night flying.
Okay, but before we get into all the, fancy systems, let's hit that reality check right away, the GA perspective.
Let's do it. Because the vast majority of light aircraft, the Cessnas, the Pipers, the planes you're likely renting or time building in often, they only have a heated pitot tube, maybe basic defrost.
That's it.
Pretty much. And they are explicitly not certified for flight into known icing conditions. Full stop. And that one fact, it seriously limits where and when you can fly cross-country in late fall, winter, early spring.
So you're up there, maybe in a 172. You see ice starting to creep onto the wing leading edge. What's the rule? What do the manuals say?
It's non-negotiable. You must exit those conditions immediately. Period.
Divert, climb, descend.
Whatever it takes.
Whatever it takes. Swiftly. The systems we're about to talk about, on more capable aircraft, they're really just tools to give you a safety margin, a window to make that exit. They're not for hanging out in the ice.
Okay, critical point established. So now let's look at the main ways more complex aircraft deal with structural ice, starting with probably the most visually distinct system, those inflatable boots.
Right, the pneumatic de-icing boots. They're basically these rubber sheets bonded right onto the leading edge of the wing or tail.
And the idea is you wait for some ice to build up first.
Yeah, you let it accumulate a bit, then you hit the switch.
And how do they actually, get the ice off?
Well, in smaller planes with boots, there's usually an engine-driven pneumatic pump. It inflates the rubber sections pretty quickly, just for a moment.
Like flexing it. Exactly. It cracks that layer of ice and the airflow just whisks it away. On bigger turboprops, they often use something more potent. Engine bleed air?
Bleed air again. That's that super hot, high-pressure air from the engine's compressor.
That's the stuff. Very powerful way to inflate those boots.
And you control it from the cockpit. Single shot or automatic cycles.
Yep. Usually a switch gives you options. Maybe a single cycle, or it might run on an automatic timer. And this brings us to that old pilot debate. The myth about ice bridging.
Ah, yes, I've heard this one. The idea that if you inflate the boots too soon with only thin ice.
The theory was, that the boot inflating would just stretch the thin ice layer, making it conform to the inflated shape, and then it wouldn't break off properly, maybe even making future cycles useless.
So, truth or myth?
Our sources are pretty clear. With modern boot designs, ice bridging isn't really a thing. You might get some residual ice left over, sure, but pilots should feel okay cycling them as soon as they see ice forming. Check your AFM/POH, obviously, but don't wait based on that old bridging fear.
Okay, good to know. Myth busted. How do you know if the boot system is actually working correctly when you're flying?
You'll have a gauged pneumatic pressure or maybe system suction, and it'll have clearly marked operating ranges. You watch that. But honestly, just as vital is the pre-flight check.
Looking for damage.
Absolutely.
Yeah.
Tears, punctures, poor bonding. These boots take a beating. Meticulous pre-flight inspection and proper maintenance are key.
All right, so boots handle the de-icing, removing ice. What about preventing it entirely? That leads us to thermal systems using heat.
Right. Heat is, well, probably the most effective anti-ice method out there. Again, on high-performance turbine aircraft, they use that engine bleed air. They pipe that incredibly hot air directly into the leading edges, wings, tail, engine inlets sometimes.
So it just keeps them too warm for ice to even start forming?
Precisely. But there are newer electric alternatives emerging too, aren't there?
Yeah, I was reading about ThermaWing. Uses electric heating.
Exactly. It's like this graphite foil laminate they apply. And the clever bit is how it uses power. It's zoned.
Zoned. How so?
Well, one zone, right at the very front, the leading edge, gets continuous heat. Pure anti-icing. Then there's a second zone a bit further back on the wing surface.
Okay.
That part cycles the heat on and off. The idea is to just loosen the bond of any ice that might manage to form there so the airflow can just peel it away. Kind of a hybrid approach.
Ah, smart. Preventative, and helps shed anything that slips through. Since these are anti-ice, focused on prevention, the rule for turning them on must be pretty strict.
Absolutely critical. Thermal anti-ice systems must be switched on before you enter known or expected icing conditions. If you wait until you see ice, you've already missed the point. You're behind the curve.
Got it. Prevention means acting first. Okay, method number 3 for airfoils. Less common, maybe a bit more old-school chemical approach. The weeping wing.
Yeah, the weeping wing, or TKS system, is the common brand name. It works by pumping out an antifreeze fluid, basically a freezing point depressant.
How does it get the fluid out?
Through thousands of incredibly tiny laser-drilled holes along the leading edges of the wings and tail.
Wow, thousands. Okay.
Sort of, yeah. Either very fine wires embedded in the glass or a conductive film coated onto it. Very effective at keeping the screen clear. But there are 2 major warnings with electric windshield heat. Pilots absolutely must know these.
Okay, lay them on us. These sound important.
First, these systems generate a lot of heat. You should generally not use them during ground operations. You can overheat the windscreen, potentially causing delamination or other damage. Very expensive damage.
Right, save it for the air. What's the second warning?
This one's maybe less obvious, but potentially more dangerous in certain situations. The powerful electrical current flowing through that windscreen. It can cause huge errors in your magnetic compass.
Huge errors, like how much?
We're talking potentially up to 40 degrees of deviation. 40.
Wow, 40 degrees. So if you're IFR, maybe hand flying, and you turn on the windshield heat.
You could effectively lose your primary magnetic heading reference if you're relying on that wet compass. It's something you absolutely have to factor in, especially if other nav systems fail. It's not a minor detail.
No kidding. 40 degrees isn't a footnote, it's a whole different direction. Okay, that's a massive takeaway. Let's move to the props. They spin fast, must ice up easily.
Extremely prone to it, yes. High speed, thin, leading edge. Again, you'll see alcohol systems or electric heat. Alcohol usually sprays from nozzles near the hub.
And centrifugal force spreads it out.
Exactly. Often helped by little grooves or channels in rubber boots on the leading edge to guide the fluid down the blade.
And the electric version. Similar to the wing boots.
Kinda, yeah. Electrically heated boots bonded to the prop blades. They usually have embedded wires and are often split into sections like an inboard and outboard section to heat things evenly. You monitor this with a dedicated prop anti-ice ammeter in the cockpit.
Okay, makes sense. What's the big danger if one of these prop heaters fails? I've heard stories.
Oh, it's serious. Think about it. If the heating element fails on just one blade, or even just one section of one blade, suddenly that blade starts collecting ice while the others stay relatively clear. You get an immediate imbalance, unequal loading, severe, potentially catastrophic propeller vibration. The sources really stress this. It can be incredibly violent, dangerous for the engine mounts, the airframe, and frankly, terrifying for the pilot.
So that pre-flight check of the prop boots isn't just looking for nicks.
No, you're looking for any sign of damage, burning, anything that suggests a potential failure. It's absolutely critical. A small fault there can lead to a massive problem very quickly.
Wow. Okay. Duly noted. And finally, just quickly, what other little bits usually get heated for instrument accuracy?
Yeah, the real basics for safe flight. Your pitted tube and your static ports, obviously. Fuel tank vents need to stay clear.
Yeah.
And your stall warning sensor. These are pretty much always heated electrically.
And the rule for checking them?
Same as always. Check them according to the procedures laid out in your specific aircraft flight manual, or POH, before every flight where icing could even be a remote possibility.
That's a fantastic rundown of some complex systems. Let's bring it all back home, especially for that PPL, maybe thinking about pushing into colder weather flying. What's the single biggest safety message here?
I think the absolute overarching rule, summing up everything from the sources, is this. All this anti-icing and de-icing gear, it is not meant for you to just drone along happily in icing conditions for hours.
Right.
These are high-demand systems. They're designed to deal with an encounter, to mitigate the immediate threat, and critically to buy you the time you need to get out of the ice immediately.
So encounter ice, use the systems if you have them and are trained, but the primary goal is escape.
Escape, that's the mission.
Yeah.
Knowing your system's limitations, especially that crucial difference between a plane certified for flight into known icing, a Fike and one that absolutely is not, that's fundamental to safe planning and flying.
Absolutely. Okay, final thought for our listeners to chew on.
Yeah, think about this. We've talked about how critical pre-flight checks are and the potentially severe consequences like that prop vibration from just one small component failing. So beyond just reading the basic POH operating procedures, what other aspects of aircraft maintenance records or documentation should pilots, especially PPLs stepping up to more complex aircraft, really try to understand before relying on these sophisticated Ds and anti-ice systems in marginal weather? Something to think about for that next level of safety.
That's it for this episode. Keep your wings level, your brain sharp, and catch you next time in the pattern. Thanks for riding with Propeller Breeze.